Fantastic. Hello, everybody. Hope you had a wonderful lunch. I had seconds. It was fantastic. And now we've got a great talk, Teaching Python with Tiny Occult Pandas. I love the title. This talk is being given by the wonderful Bruce Fuda. And prior to his role as a computing education specialist at the Australian Computing Academy, Bruce was acting as an associate principal of a government college in the ACT with a population of around 1,200 students in years 11 and 12. Wow.
That's big.
That's big. Please welcome Bruce to the stage.
Thanks for that. Thanks, Donna, and hello, everyone. It's great to see the developer community come along to support a talk on education at a developers conference. I've presented a couple of PyCons in the past as well in the education track, and it's always good to see that the developer community really supports the work that we're doing in schools, and specifically the way that we're using Python to help students learn not just computing, but a lot of other stuff as well, which is kind of where this talk is going to go. So a little bit about me. I'm currently working as a computing education specialist at the ACA, which is a centre at the University of Sydney. I've been a teacher for a little over 13 years now, and I guess before I began teaching, I was doing a little bit of web development, and I continue to do that, mainly working with Flask. And the other sort of bit that I did while I was teaching was I contributed to the writing of the Australian curriculum in digital technology. So my sort of experience is definitely very heavily education biased, but I think being involved in that curriculum writing process and understanding exactly the barriers that schools are dealing with when it comes to implementation of the new digital technologies curriculum is something that sort of allows me to understand some of the challenges that we're facing and a little bit more about the pipeline that eventually leads into the development world. So I'm going to start by providing a little bit of context because I think that's important to understand before we get going. And I'm going to talk very briefly about what the curriculum F to 10 does and how that relates to what's happening in senior secondary education. I'm going to be using the ACT as my context, but I want to emphasize that the work we're doing, whilst it will be directly aligned to the expectations in the ACT, is starting to, I guess, converge on a consistent set of expectations in year 11 and 12 across the country. And whilst New South Wales will potentially be one of the last states to get there, being the largest of the jurisdictions, I expect we'll see a lot of common elements across all of the senior secondary education expectations. So the F to 10 curriculum is built on 10 concepts, and those concepts are centered around abstraction, data, algorithms, digital systems, and interactions and impact. And basically, the intention is that students are not just learning to write code, but they're understanding how code fits into a broader context of the way we interact with computers, how that has changed the way that we interact with one another, and at the same time, understanding the nuts and bolts of how automated solutions work and some of the challenges associated with that. So I guess that abstraction underpins all that we do, and then we have individual sort of outcomes and expectations that relate to those other topics. Now, in terms of the programming specifically in F to 10, we start out as early as foundation or kindergarten, and from kindergarten to year 2, the exposure to programming generally starts with kind of physical stuff. So you may have seen B-bots or those kind of toys where you press the buttons and they follow those paths around the floor and do that kind of thing. That's kind of the extent of what we want students to be experiencing, and it's really all about understanding algorithms and the steps involved to achieve a goal, usually something to do with moving to a specific place. In year 3, 4, and 5, 6, we want students to start to actually write code, but they do it using visual programming tools like Scratch. So if you've ever seen block-based coding, and Scratch is probably the sort of #1 platform that's used worldwide, this is where we start to introduce those ideas of branching and iteration and get students to come up with algorithms that aren't always going to achieve the same result, right? There's some kind of difference in outcome as a result of the inputs that get added to the program. In year 7 and 8, we introduce the concept of functions and move towards text-based languages. And a lot of the work that we do at the ACA suggests that teachers use Python because it is a really great language to learn, and it's extremely powerful, which means you can continue to use it right through to senior secondary education and beyond. which is why in Year 9 and 10, when object-oriented programming it begins in terms of curriculum expectations, and that is an elective subject, so not every student will necessarily do this. But Python supports OO, without and the need to go out and learn another language. So if schools are using another language instead in Year 7 and 8, they find very quickly that they can't meet those curriculum expectations and they need to switch it again. So the fact that you can do everything in Python means it's a really good choice through high school, and that's kind of why a lot of the work that we're doing in Year 11 and 12 in the ACT is sort of built around the assumption that Python is going to factor in somehow into the planning. So in Year 11 and 12, the curriculum structure in the ACT is quite unique. It differs significantly from what you might be familiar with if you know anything about the New South Wales system or Victoria. And that is because the curriculum is built around what we call a framework, and that framework captures all of technologies. So that's not just computing, but it's everything from fashion and textiles through to engineering and woodworking and all those kinds of things as well. So because we have common assessment expectations with those subjects, we need a way to differentiate between what IT does and what they do. So we have two course areas. And the course area of IT builds on those concepts I talked about from the F to 10 curriculum. And then we have a course area called Design and Technology, which deviates a little bit and builds on what we call the Design and Technology subject from kindergarten from up to Year 10. And then within those course areas, we have individual courses. And this is what my talk is going to focus on today. So in the IT course area, the 4 courses we have in the ACT are data science, digital technologies, robotics and mechatronics, and networking and security. And there are a stack of design tech courses as well. But like I said, they're a different subject area. Their expectations are very, very different to what we would expect in an IT course. So the other thing that's interesting about the ACT is all of our courses are written by the teachers in the jurisdictions. And we do that on a review sort of rotation of about 5 years. So every 5 years we get together, we consider what's been popular in the previous iteration of the courses, and we rewrite them. And before this rewrite, which has only just happened, we had a single IT course which had 27 individual options that you could do. So now we have 4 courses, and each course has 4 units of study. We have a data science course which starts out with data representation and analysis, continues on to do some big data analysis and the techniques associated with that, machine learning in the first part of Year 12 and finishing up with a data research project. In digital technologies, the course is a little bit more general in nature. The idea here is that students can potentially learn a number of different things. There's no need to sort of lock into a single platform or technology. But generally, this is where students might say, start out in digital assets, understanding the bits and pieces that might make up a web application. They move into digital systems to start thinking about how those communicate with one another or how they integrate. In digital solutions, they're turning that into a full-blown application. And then in the final project unit, they have a chance to really sort of go out, take that knowledge and build something of their own. So it's not as scaffolded as it might be when we're talking about the earlier units in the sequence. But they might do that with games development or something else instead. Networking and security really does focus on that networking element of constructing a network, understanding the network model, how we design networks to be secure and enable the communication that we want. And they finish up ultimately getting an understanding of distributed computing and cloud. And this course is probably the one that brings with it most of the legacy work. So prior to this course existing, we had 4 units written in the old course that were sort of mapped to the Cisco Certified Network Administrator course, and a lot of that stuff is still present in this course as well, because it does prove to be popular with a small group of students in the ACT. And then our other course, Robotics and Mechatronics, starts out with sort of understanding circuits, building and programming those circuits, moving through to how we deal with different types of data and the interactions that occur in those circuits when we're using that type of data. We look specifically at the challenges associated with building robotics and mechatronics systems, and then finish up with an opportunity for students to think about the applications of robotics to different types of problems. So there is also a negotiated unit of study, and one of the things that we talked a little bit about on the education track on Friday was the fact that there are we always deal with a very diverse population of students. So you have some students who are very, very capable and confident, and you have some students who are doing this for the very first time and may not even have been exposed to these concepts in high school. So that negotiated unit of study allows the teacher and the student to work out what is an appropriate expectation for them, and we can come up with a project that's going to be within scope and challenges them in a way that's going to suit exactly what they need. And we have that option available to us in every course. But because that's not already complicated enough, we add another layer. So we have the option over the 2 years for students to do 2 of these courses. They're able to sort of combine these to create what's called in the ACT a double major, which means that their IT counts for a greater proportion of their ATAR score if they're seeking, a university placement. And so that also means that we've got flexibility in schools and for student enrolments to borrow units from different courses and combine them to create this double major. So you could, for example, do all 4 units from data science and all 4 units of digital technologies and get a double major in that way. And that sort of makes sense if those are the 2 areas you're interested in. Equally, for whatever reason, a school may not have the population, or students may lose interest partway through, and they may switch out and do a couple of, say, robotics units instead of the later units in data science, and that's also a valid sort of package for them by the end of year 12. You could do a bit of everything, so that's also perfectly valid. Or if for some reason you're kind of crazy and wild, you can do some weird combination like this. Now, obviously, some of these are valid in terms of the rules, but they're not practical. I mean, you're not going to be able to necessarily go out there and do an applications of robotics unit if the only thing you've done is built basic circuits. Similarly, you're not going to be able to do a machine learning unit if you've done nothing at all with data previously. So there are practical limitations on these combinations, but the reality is we can see students borrowing from lots and lots of different courses. And that has a number of complexities that we need to deal with. That is going to be the focus of the second part of this presentation. So as we move into 2020, which is when these courses are going to kick off, we've got a number of challenges, but they also bring with them a number of opportunities. And the first thing I want to emphasize is that curriculum is an imperfect abstraction. And the best way to demonstrate this is to look at a specific course, and I'm going to do it with data science. So this is one of our content descriptions, or sort of teaching points, from the data representation and analysis course, and it says we want students to investigate and define the requirements of a problem and select, acquire or generate the data necessary to solve it. If we look at the equivalent content description in big data analysis and techniques, it's investigate and define problems typically solved by large data sets and select and acquire the data necessary to solve them from large data sets. And in machine learning, we have a very similar paragraph. Investigate and define problems appropriate for the machine learning domain and select and acquire the training and source data necessary to solve them. Now, if we look across these 3 content descriptions, that's really the only difference. There's not a whole lot of differentiation between those expectations. And this is fine if you know what all of the words mean. Okay, but if you don't, and you're a teacher who's never done this before, understanding what those subtle expectations are is going to be really hard. And the thing is, even if you know what they actually mean, it's still pretty loose. So it's not telling you exactly what it is you want students to learn in terms of, a machine learning domain and how you define that. But the expectation is that teachers are going to make those adjustments as appropriate. And that's, like I said, okay if you know what these words actually mean. So this is how a lot of teachers are feeling right now. There are a lot of changes happening in this space. We've got a number of challenges, and the first of those is reorganizing any existing content we have, because when you go from a sort of choose your own adventure of 27 different topics into a sequence of 4 that are related in some way, you need to work out what you can keep and what you can throw away and whether the order of teaching has changed. There is a stack of new knowledge built into these 4 courses that a lot of teachers just don't have. We've got a stack of different languages that are being used across the different colleges. And a good example of that is that a lot of the robotics that is done in the ACT is done on the Arduino platform. So, it's a well-known platform. There are a lot of hobbyists doing it. There are a heap of resources. It's established. And if you look at what we'll be using in data science, where Python really is dominant, then if we've got students picking and choosing across the two, it brings with it a lot of complexity. We've also got topics we've never taught before. Some of us have taught bits and pieces, but we don't know where the resources are. We don't know where to start. And then there are also the challenges associated with assessment and making sure students actually know what it is that they're learning, and then moderating that assessment across schools. Because one of the other unique elements of the ACT is because we're so geographically and small and we have such a small population, we don't have a standardized exam. So you don't go and sit the HSC exam and as a result need to have taught or learned exactly the same across every school to give everyone a fair sort of opportunity to achieve. And instead we do that through a process of moderation, where we simply demonstrate what we see as an A grade at our school with an A grade at another school, and we use a scaling test to just get a sense of what the differences are between, say, an 80 at one college and an 80 at another. Now, that only works because we're a small jurisdiction. It doesn't work in the larger ones, but it is a challenge. So, the three solutions that we need to really focus on are teacher training, resourcing, and assessment samples. And the thing is, teachers are able to very, very easily focus on 1 and 3. But when you don't know a whole lot about the area, you're going to need some help with 2. And so that's what I'm talking about. I mentioned the fact that all of the units could potentially work with different languages and different content. That brings with it a significant cognitive load. And the ability to combine them is great for students because it gives us a lot of flexibility. And like everything, when something is great, it's good until it's not anymore. And we need some way to create some order from the chaos that can occur in this instance. So what we do is, as teachers, we need to manage the assumed knowledge that students bring into a unit. And I mentioned that a little bit before with how can you understand the cloud if you don't understand networking generally. Is it better to be able to write an if statement in 15 languages and do nothing else? Or is it better to really grok one language? And how do you make sure that that is something that you build into your design of curriculum? And obviously there are a number of logical and structural differences between the languages that might be used in different domains as well. And so if you've got to continue to relearn that stuff, you're constantly having to sort of understand or add that additional layer to what you're trying to process at any time. And so to create that order, really teachers will have a look at where we can kind of find common elements and build those into the foundation courses so that students are able to build on knowledge that they're able to have already experienced. And that's where Python, I think, is really powerful because it now really could be seen as being a unifying language for all of those courses. I mean, it's obvious in data science that Python is a good choice. There are so many frameworks and APIs that we can use to collect or to access and manipulate that data. Digital technologies, the web is often used as a platform in that subject. So frameworks like Flask and Django work really, really well. And a lot of the sort of front end side of the web is well done in schools, or at least has a history. So the only thing Python's particularly weak in that area is in games development, but it can't be good at everything. Robotics and Mechatronics, now that we have Micropython, is almost a solved thing. I mean, typically, like I said before, Arduino dominates, but everything that's done in the Arduino projects can be done in Micropython. The only issue is the resources and the examples and the code samples and all the other bits and pieces that we need to make that a reality don't exist because it just doesn't have the legacy that Arduino does. And then networking, look, it's not my area of knowledge. It's not something that I've taught before. I've got a colleague who's written that course. What I do know is Cisco is using more Python now than they used to, but most of the work that's done focuses on system administration of networks. And so often the question is, why would we bother with, introducing Python, because you can do most of this with configuration files in Linux. So what's the point? So these are all the things that we're fighting, and I guess what we're trying to do for teachers now is come up with sample activities that demonstrate how Python can fit into a teaching program in all of these subjects. And I want to start with data science. Ultimately, this is all about, the course generally is about helping students find meaning in data. And that means understanding visualization, pattern analysis, investigating APIs, and performing programmatic analysis on large data sets. Basically, it's all about students being critical of the results that data presents and understanding what those results mean. And so we actually start out pretty early on with things like Google's Public Data Explorer. It's just really nice to be able to look at a visualization, and you can see I've sort of identified a couple of countries who, over this time series, have some significant changes in the graph here is the fertility rate and life expectancy. And so you can see very quickly that when China brings in the one-child policy, their fertility rate drops significantly. And you can see periods of genocide in a few different countries when those dots really fall off in terms of the life expectancy. And so we want students to understand that often visualizing data is a way to create enough of a question that you can then investigate, and that's the bit that we want to explore. Obviously, correlation and causation is a concept that's really important for students to understand. And if you've never seen the correlation, the Spurious Correlations website, it's worth a look. There are some really interesting data sources there. Apparently, the number of times that Nicolas Cage appears in a movie in a year is also related to the number of suicides that occur in the US or something like that. So yeah, these ideas are things we want students to be interested in, and we want them to then be able to explore them in a meaningful way. And so Pandas is obviously a really nice way for us to be able to connect students to data, structure it in a way that is easily manipulated and analysed. And I think we've got really good examples of this, and I know Zach Hatfield-Dodds presented yesterday. He's got some tutorials that we've actually sort of taken and used and built into resources that allow students to connect to 20 gigabyte databases and then generate really nice visualizations like this one, just using Pandas and the stuff that's built into Python. So there are a stack of other things we use to explore data science, everything from Excel through to things like NLTK if we want to work with natural language. But there is going to be heaps more. And it's you in the audience that are working in data science that know what all the other great things that we could use are and that are out there. Now, digital technologies is more that kind of software development side of things, programming, UI, UX, and understanding how challenging it can be to collaborate on a project with multiple people. But ultimately, it's all about building solutions to user problems and doing that with software. So to introduce students to programming, we subscribe to Grok Learning at Gungahlin College, and now that the ACA has produced a lot of resources that are freely available to students, it's a really good start in terms of getting the basics of Python down. There's also Pygame. I used it in the past. It's really good to see that active development seems to have picked up again. At one point there, the sort of 2 to 3 Python version change combined with some of the changes to the way that Apple were doing stuff on the Mac and other bits and pieces meant that there were a sort of big delay in terms of updates on this project. But it appears that this may become viable again for us to do some games development stuff, which is really cool. And I mentioned Flask before, and the fact that there are some really good resources for Flask, like, for example, the Flask mega tutorial, which is broken up into something like 26 individual steps and starts out really, really basic, and even introduces things like setting up virtual environments for students. Those are the kinds of resources that we can take and turn into really valuable teaching activities, and then go on to form the basis of projects, like students building their own sort of collection management type platform for, could be anything, everything from sort of, keeping track of Pokemon or just managing a movie collection. So again, depending on what students are doing, plenty of frameworks and tools out there that they can experiment with, depending on the nature of the activity. And again, those of you who are working in software development and are building interesting things and are finding that there are some really great platforms and frameworks to be engaging with, that's the stuff we want to know about. And we want to know the kinds of things that work really, really well for getting you started with something that you don't necessarily know a lot about. Robotics and mechatronics, like I said earlier, starts out at circuit design. Ultimately, it's about automation to address physical problems in the physical world. And of course, all the challenges associated with hardware that you don't have to deal with in software, like two identical motors, or they look identical, but they behave very, very differently when you provide the same voltage to them. Those are the kinds of challenges that are unique to this domain. And I've already mentioned that Arduino is the dominant platform in ACT schools. We are seeing a move towards Micropython, sometimes using the microbit, sometimes using things like the PyBoard. Either way, the cool thing about Micropython at the moment is the documentation and the tutorials that come with the documentation are really good as a starting point for us to use in schools. But beyond those tutorials, when you start looking at what's out there for project ideas and the like, it's a little bit limited when you compare what's out there with Arduino. And so we've got access to things like Grok Learning to assist with the syntactical sugar associated with that, and they've got some additional projects that we can pick up and use. But ultimately, we want students to get out of the platform and build their own stuff, use something like the Mu editor, so that they can start interacting with Micropython in the same way that we have them interacting with other software. And again, heaps of things that we can access, but our biggest challenge in terms of getting more Python into robotics is examples that teachers can grab and use as the basis of potential assessment items. Which brings me to the last course, which is networking and security. As I said, not an area of strength for me in terms of content knowledge, but what I do know is that really the course is about students understanding all the technology associated in the facilitation of communication between people, and that means understanding both physical and virtual networking, as well as how data transmission works, and the security implications of all of those things. So the Cisco Networking Academy really is the go-to resource for teachers in this area right now. And as I said, they're doing more Python, but there's also a lot of sort of understanding all of the composition of how packets move around on the network and what a packet looks like and all that kind of stuff. So things like Wireshark are often used in this course. And then we've got things like Ostinato, which is a packet generator, which actually allows students to build a packet from the ground up and then to change that packet and send it again to see the different responses that you might get. And what's interesting about Ostinato is that it's got a powerful API attached to it that is written in Python, and that allows us to do network test automation. So we're seeing schools picking up Ostinato purely for the purpose of giving students that experience generating their own packet and building it up from scratch. But it means that we can also start looking at how we can say to students, you know what, it makes sense to automate a lot of your testing so you're not building these packets from scratch every single time, and programming gives you a mechanism through which you can do that. And we can do it with Python. So it's another avenue for us to potentially inject more Python into the networking course. But the reality is there's a lot of unknowns in terms of how Python can feed into this, and that's where we need a lot of help. And that's where I'm going to finish up this presentation. I'm going to tell you the ways that we can get some support from you. And really, we want to make the experience for students the best it can be, regardless of what subject they're going to take, what course they're going to study. So specialisation, it turns out, is a thing. In the room today, we've got this group, which is all of you. You're the developers. You know this stuff well, and you use Python and a stack of other tools to do real things. All right? On the other side of the fence, there's us teachers. It turns out we know how students learn really well, right? And we can take resources that we find that are really good in terms of communicating an idea or building up an activity, and we can turn it into something that students can actually learn from, even if they haven't had a whole lot of prior experience. Now, there are a few people, these teacher developers that sit in the middle here, and I guess I would count myself as one of those, but the reality is there aren't many of us. And if I think about the number of teachers in schools who are teaching these topics and are now in a situation where they're going to have to redevelop these courses, most of them are really sort of going in blind, and all they know is what they've been teaching for the last sort of 5 or 6 years. So we've received some funding as Information Technology Educators ACT to pulls teachers out of class to build up quality resources that we can distribute to schools and teachers and be confident are going to address the expectations of their curriculum. It's been really lucky. We achieved that through one of the grants that Google provides. And what I'm asking of you today, and anyone really, is to contribute to the work that we're doing. Now, we don't care what your contribution is. There may be great tutorials, there might be useful frameworks, you might have really good resources for explaining particular ideas and theories, or you might just have some really cool code samples that do interesting things in these 4 domains. They do not have to be classroom ready. We've got specialists, us teachers, who know how to turn something into a resource that can be used in the classroom. But what we don't know is what's good in the developer world. You do. So we have this GitHub repository attached to me at the moment, which is really just a dumping ground for all of the cool stuff that does data science, networking, robotics, and anything else to do with application development. And we've got separate folders set up for each of those. There's a README file that explains what the internal structure is for. Basically, there's a section, a contrib folder in each of those that is specifically for, hey, this is cool. Don't know if you can use it, but take a look. All right? And then we've got folders separately for, this is a resource that we just need to tweak, this is ready to share for teachers. And that's the kind of thing that we want you to submit things to. All you need to do, grab a copy, submit a pull request, bang, we've got it. All we need is as many contributions as we can get. If we got 1 contribution from every single developer at this conference, we would have more than enough resources to be able to build really, really good education programs for all of these students. The other way you can do it is just to email a link to contribute@intiac.act.edu.au. If it's just a URL to a website, that's going to be easier. There's no need to go through the process of setting up a pull request. Perfectly fine. We'll manage it from our side, but I really can't emphasize enough that the resources we're building are going to be published. They're going to always be free. They're always going to be open. We want these used by as many teachers across the country as we can. Yes, we're building them for the ACT, but the intention is that eventually we'll have teachers in every state in Australia, potentially around the world, using this stuff and contributing to this repository, so we've got a really good collection of appropriately pitched resources for teaching these concepts to students. So that's it from me. Thank you everyone for your attention this afternoon. Please share those links and that repository with your colleagues. If you know someone working on something really interesting or who's involved in actively sort of engaging with a data set that you know is going to have some stuff that students are going to want to engage with in it, please let us know. We'll do the hard work. All we need are the signposts to the right things that we can then build into those resources. Thanks a lot.
Thanks so much, Bruce. You do an amazing job, and this is a little gift on behalf of